Welcome to NEET one short series, that is lecture number 4. So today we are going to discuss system of the particles and rotational motion. So we'll try to cover some of the basic concept and basic formulas related to this chapter. So let's see. How many questions that has been asked from this, that is number of questions asked from the center of mass. So this chapter is divided in two parts. First is system of particles and second is rotational motion. So system of particles contains this center of mass as well as collision. Over the years we can see that how many questions they have been asking from this, that is one or two questions we can definitely expect from this, that is two questions, one question, two question, one question. Different questions are asked over the years from which topic? Center of mass and collision. Second, if we talk about this, that is rotational motion. So in rotational motion, how many questions they are asking? Again, two questions per year they are asking, starting from, if you compare this 2015 to 2024, we are expecting two questions from the rotational motion as well as we are expecting two questions from this center of mass and collision, one or two questions. Overall, this chapter, little bit bigger chapter for NEET, we are expecting approximately 3 to 4 questions this year as well. So let's begin our journey of today's revision class, that we are going to discuss what is center of mass and collision. Second thing is that what is rotational motion. So if we talk about the center of mass, we have certain topics over here. That is the position of the center of mass. So for example, different bodies are there, different points. We define position of center of mass is given by RCM. What is RCM? M1 R1 plus M2 R2 plus M3 R3 divided by total mass M1 plus M2 plus M3. So here R1, R2 and R3 are the position vector of the mass M1, M2 and M3. Corresponding, if you write break in this term, that is in terms of the axiom, that is x coordinate of center of mass, we'll be writing this M1 x1 plus M2 x2 plus M3 x3 divided by total mass is M1 plus M2 plus M3. Corresponding, if you write YCM, what is YCM? M1 y1 plus M2 y2 plus M3 y3 divided by total mass, that is M1 plus M2 plus M3. These are the axiom and YCM. Corresponding will be writing for ZCM as well. So this is for different masses are placed at different position. This will be x coordinate of center of mass and this will be y coordinate of center of mass. Suppose if they are asking continuous mass distribution, if they have given continuous mass distribution, so what is continuous mass distribution? For example, like we have the ring where the mass is distributed continuous over its circumference. We have the disk where the mass is distributed completely over its area. We have this sphere where the mass is distributed completely over the volume. So like that we have continuous mass distribution. So for a ring, if you have a ring, what is center of mass? Exactly the center. If you have a disk, what is center of mass? Exactly at the center of the disk we have center of mass. If you have rod, rod is also motion of center of mass of the rod is also exactly at the center. If you have this sphere, solid sphere, center of mass will be exactly at the center over here. Even if it is hollow sphere, center of mass will be at the center. So these are the center of mass we have for the solid sphere as well as hollow sphere. And if you have semicircular ring, for the semicircular ring, distance of the center of mass from the center of the original ring, that will be given by 2r by pi. So this particular point distance is given by 2r by pi. If we have semicircular disk, this disk is there. From this center, if they're asking what is distance of center of mass from here, this will be 4r by 3 pi. Is that clear, all of you? This will be 4r by 3 pi. If you have hollow cone, if you have hollow cone, right circular cone, distance of the center of mass from this is, if it is hollow cone, this will be h by 3. If we have solid cone, distance of the center of mass from the base is h by 4. If we have solid cone, from its base is h by 4. So these are we have for the center of mass, different formulas as well as continuous mass distribution. Second topic is that we have motion of the center of mass and conservation of linear momentum. What is motion of the center of mass? If bodies are moving, two bodies are there, M1 is moving at velocity v1 and M2 is moving at velocity v2, then what is velocity of center of mass? So here we define, that is velocity of center of mass is given by M1 v1 plus M2 v2 plus M3 v3 divided by M1 plus M2 plus M3. What is acceleration of center of mass? that is m1a1 plus m2a2 plus m3a3 divided by m1 plus m2 plus m3. So this is acceleration of center of mass. This is the velocity of center of mass. Now, if we talk about the how the conservation of moment, linear momentum happens, and how can we correlate this with center of mass. So for example, for any given particle, different masses are there, m1, m2 and m3, m4. Different masses are there, and the force is acting on the particle. So in that case, we'll be writing this. Different forces are acting over here. So whatever the forces that is acting between m1 and m2, m2 and m3, if I take this m1, m2, m3, m4, this all is one single system. Whatever the forces that is acting between m1 and m2, m3 and m4, m1 and m4, that is all the between the bodies, whatever the forces that is acting will be called as internal forces. And whatever the force we are applying together on all of these masses will be called as external forces. So if external force on the system is 0, remember this, if the external force on the system is 0, then what we define? Linear momentum of the center of mass will be constant. So what is external force? From the Newton's second law, we know that F equals to dp by dt. So in this case, we'll be writing this dpcm divided by dt. What is pcm here? Linear momentum of center of mass. So this particular term is 0. So if this particular term is 0, means I can say that if this one is 0, so this dpcm by dt is 0. So from here I can write pcm is equals to constant. Because this is 0, then moment of center of mass will be constant. So what is linear momentum of center of mass? M into VCM, that value will be constant. M into VCM, that will be constant, where M is the mass and this is the velocity of center of mass. If initially center of mass is at 0, then final velocity will be at 0. If VCM is 0 initially, then finally also VCM final will also be 0, because velocity of center of mass is constant. Next we have collision. So collision is divided into, so suppose any type of collision in given NEET questions, we can always do conservation of linear momentum. So conservation of linear momentum, mass m1 u1 plus m2 u2 is equals to m1 v1 plus m2 u2. This is the conservation of linear momentum, that is momentum before collision should be equal to momentum after collision. Second is coefficient of restitution. What is that? Velocity of separation divided by velocity of approach. So this u1 and u2 are the velocities before collision, and v1 and v2 are the velocities after collision. So this, if you talk about the coefficient of restitution, that is E is given by v2 minus v1 divided by u1 minus u2, and we can take it mod over here. So this u1 minus u2. So collisions we can divide into 3 parts. That is, first one is elastic collision, perfectly elastic collision. So in perfectly elastic collision, what happens? The coefficient of restitution value is 1, E is equals to 1. Second, that we can write that kinetic energy initial before collision, kinetic energy initial equals to kinetic energy final, that is after collision. Initial kinetic energy should be equals to final kinetic energy. No loss of energy in this case. Perfectly elastic collision. Then we have inelastic collision. So if we have inelastic collision, inelastic collision, what is E value? E value will be less than 1, greater than 0. It will be less than 1, greater than 0. Kinetic energy initial will always greater than kinetic energy final. So there is loss of energy after the collision. That loss of energy can be in form of heat, or can be in form of light, or can be in form of sound as well. Third part we have, that is perfectly inelastic collision. So in this case, what actually happens, that perfectly inelastic collision, after the collision both the bodies will stick together. So mass m1 moving at the speed u1, mass m2 it will moving the speed u2. After once they are collided with each other, they will be moving together. That is, m1 and m2 will be moving together with common velocity. That is common velocity we define. So here the coefficient of restitution will be 0, because there is no separation. Separation is 0. So in this case, and second is kinetic energy is initial should be equal to kinetic energy final. So here we define that is E is equals to 0, and this initial is greater than final, loss of energy is there, and common velocity will be writing this VCM, or we can write it, common velocity, final velocity we can write here, V is equals to m1 u1 plus m2 u2 divided by m1 plus m2. And there is one direct formula that you can note down for this collision part, that is velocities after collision. Velocities after collision, that is given by velocities after collision. So mass m1, it is moving with the speed u1. Second mass m2, it is moving the speed u2. They collided with each other. And after collision, mass m1 will move the speed v1 and mass m2 will move with speed v2. Then what are the velocities v1 and v2? You can note down here. So what is v1? We will be writing this m1 minus e m2 into u1 divided by m1 plus m2 plus, I'll be writing this. This will be 2 m2 u2 divided by m1 plus m2. So this is the velocity v1, that is after collision. Corresponding can write v2 as also. So what is v2? m2 minus e m1 into u2 divided by m1 plus m2 plus 2 m1 u1 divided by m1 plus m2. So this is the velocities that is after collision. So and what is E here? E is the coefficient of restitution. So even if you know the formula well and good, we can solve the problem quickly. So moving next, let's solve some of the problems from this, that is center of mass. So here we define, that is three masses are placed on the x-axis. First is 300 gram at the origin. Second is 500 gram, x equals to 40. So draw this side, x equals to 0. This will be x equals to 40 centimeter. And third one, x equals to 70 centimeter. The first one is, that is 300 gram mass is placed. Second is 500 gram. And third one is 400 gram over here. They're asking what is the position of the center of mass from the origin. So what is XCM formula? That is m1 x1 plus m2 x2 plus m3 x3 divided by m1 plus m2 plus m3. Putting the values, 300 multiplied by 0 plus 500 multiplied by 40 plus 400 multiplied by 70 divided by total mass. So what is total mass here? We can write 300 plus 500 plus 400. So total mass that we will be writing here, that is this 2000 plus 2800 divided by total mass 2800 plus this is 4800 divided by 459 plus this 1200, 0 0 cancel. We are getting this how much? 40 centimeter we are getting. That is option A. So this center of mass, basic question, this came in NEET only. The question which I solved, that is came in previous year on NEET only. Just basic formula based question. Second, we have two bodies of mass 1 kg and 3 kg have the position vectors they have mentioned, that is R1 and R2 they have mentioned over here. They have mentioned the position vector R1 and R2. What they are asking? Center of mass of the system as a position vector. What is formula here? We have RCM. What is RCM? M1 R1 plus M2 R2. Only two masses are there. Just stop here. M1 plus M2. Putting the value, M1 is, that is first mass is having 1 kg. So 1 into this I cap plus 2j cap plus k cap plus. Next, second mass is having how much? 3 kg. 3 into. So 3 into this side minus 3i cap minus 2j cap plus k cap divided by total mass. What is total mass? 1 plus 3. So solving this, this is, we are getting 3 into minus 3, that is minus 9. Minus 9 plus 1, minus 8 I cap. This one is 2. 3 into minus 2, minus 6. Minus 6 plus 2. We are getting this minus 6 plus 2, that is minus 4 j cap. And this one is k cap plus 3 k cap. So this is plus 4 k cap divided by 4. We are getting this how much? The final answer we are getting here minus 2 I cap minus j cap plus k cap. That is final answer, minus 2 I cap minus j cap plus k cap. Again the answer is option A. Again the simple formula based question that is asked from this chapter. Even the student feel the chapter is little bit difficult, but still we can solve the questions. That is coming from the formula based only here. Two particles A and B initially at rest. As per the given question, two particles A and B initially at rest move towards each other under the mutual force of the attraction. They are moving towards each other under the mutual force of attraction, means whatever the forces that is acting on them, that is internal forces. They are not the external forces. Whatever the force that is acting, that is the gravitational force. A is applying on B and B is applying on A. No external force acting. So no external force is acting means what I said, velocity of center of mass will be constant, right? So velocity of center of mass will be constant if external force is not acting. Initially, if velocity of center of mass is 0, then final answer it will be 0. The answer is 0 only. Velocity of center of mass is constant. Initially, both are at rest. So center of mass will also be at rest. So finally, also center of mass will be at rest. So answer will be 0. Is that clear? Moving further. So here the question is coming from the impulse. And what is impulse? Change in linear momentum. So impulse is defined as, J is defined as change in linear momentum. So if you see one particular question over here, mass is coming with velocity v. So if we talk about, if we take the component, so this side component will be given by mv sine 60, and this side component will be given by mv cos 60. Now mv sine 60, mv cos 60, and the ball is going this way. In this case, the component will be going this side, that is mv again cos 60. If we take the component this side, and this side if I take the component, that is mv sine 60. One component along the wall is not changing because there is no force acting on this side, and one component along this side, that is mv cos 60. Again this side mv cos 60. So what is change in momentum? The final momentum minus initial momentum. The final momentum is mv cos 60. I am writing minus because it is moving towards left side, minus initial momentum minus this formula, that is mv cos 60. So this I will be writing this. This is minus mv by 2 minus mv by 2. Answer is minus mv. And if they are asking magnitude, we can directly put this option A. Clear? So secondly, here we have the question is saying that a shell of mass m is at rest. Initially, it exploded in 3 fragments having the mass in the ratio 2 raised to 2 raised to 1. So if we talk about the, let's say there is a shell, and this shell is having mass. It is exploded. This question from the explosion. Explosion happens because of the internal forces. Because of the internal forces, explosion happens. So no change in momentum of center of mass. So we can consider the linear momentum of center of mass. It broken like this. So this one is 2 kg, okay, and this one is 2 kg, and this will be 1 kg because it broken in the ratio 2 raised to 2 raised to 1. So this will move in this direction with velocity v, and this will move with this direction with velocity v. So what is momentum this side? 2 into v. What is momentum this side? 2 into v. They fly off along the mutually perpendicular direction with the speed v. What about this? So what is initial momentum? 0. Why it will be 0? Because before explosion there is no external force. Whatever explosion happens because of the internal forces of the particles here. So before explosion no internal force, initial momentum will be 0. Final momentum should also be 0. To balance that momentum, final to be 0, this side 2v, this side 2v. Resultant of this 2 will be along this direction, 2 root 2v, because this one is 2v, this one is 2v, this will be 2 root 2v. And this momentum should be balanced by this side. So 1 into v dash, mass into velocity v dash. So 1 into v dash should be equals to 2 root 2v. So from here we are getting this. What is v dash? 2 root 2v. That's it. So this is the final answer for this 1 kg mass that is moving with this much velocity. Two identical balls A and B. Two identical balls A and B having the velocity of 0.5 meter per second and minus 0.3 meter per second respectively collide elastically in one dimension. The velocities of B and A after the collision. So they're asking the velocity of ball A. It is moving with 0.5 meter per second, and this velocity of ball B, it is moving with minus signifies the direction. How much? That is 0.3 meter per second. So remember one thing, if the masses are same and the collision is elastic, if the masses are same and collision is elastic, the velocities will be interchanged after the collision. So velocity of this ball will be given to this, and velocity of this ball will be given to this. So once they will collide, what will happen? After collision, this ball B will move with a velocity of how much? Ball B is having velocity of 0.3 meter per second. The ball B, after collision, this is ball B and this is ball A. The ball B will move with a velocity of, it will gain the velocity of this one, 0.5 meter per second, and this ball A will gain the velocity of this one, that is 0.3 meter per second. What they're asking? The velocity of B first. Remember this. Sometimes statement is framed in a first, that B first, then A. So velocity of B is 0.5 positive. It will be positive because it is moving towards positive x-axis. If you talk about this ball A velocity, that is minus 0.3. Why? Because it is moving towards negative x-axis. Velocity of B is 0.5 meter per second, and A will be minus 0.3 meter per second because it is moving towards left side. Second question, from again the question is coming from the collision. A moving block having mass m collides with another stationary block having mass 4m. So there is moving block, this having mass m, it is moving with, let's say, speed u. It's colliding with another stationary block having mass 4m. Let's say this is stationary, the dimension means what is this? This is at rest. So u1 is equals to u, and what is u2 value? 0. u2 value will be 0. After collision, what will happen? What is happening after collision? When the initial velocity of the lighter block is v, then the value of the coefficient restitution is given by. So initial velocity dimension here, that is v. This dimension is v, and this one is stationary. The lighter blocks comes to rest after collision. After collision, the lighter block comes to rest. Means this particular point, velocity v1 will be 0. Of this particular block, velocity v1 will be 0. But what about 4m? They are not mentioned. Let's calculate that. Let's say this is moving with velocity v2. So here we can write conservation of momentum, that is m into u plus 4m into 0 is equals to m into v, m into this one is 0 plus this side 4m into v2. Okay, 4m into v2. So this particular term will be 0. We are getting this m into u is equals to 4m v2, m or m cancel. What is v2? U by 4. So if we talk about this, what is the velocity of, what is the coefficient of restitution? E is equals to v2 minus v1 divided by u1 minus u2. That is v2 we got how much? U by 4 minus v1 is 0 divided by u1 minus u2. What is u1? V or u minus 0. We are getting this how much? 1 by 4. Okay, 1 by 4. So 1 by 4 we are getting, that is coefficient restitution value 1 by 4. That is how much? 0.25. This will be coefficient of restitution, 0.25. So this is how we will calculate this. Okay. So one more question from the collision, last question from the collision. What they are asking here? Body A of mass 4m moving with the speed u. Body A of mass 4m, it is moving the speed u, collides with another body B of mass 2m, initially at rest. So this one is at rest. So u2 value will be 0, but u1 value is u only. The collision is head-on and elastic in nature. The collision is head-on and elastic in nature, so E is equals to 1. After the collision, the fraction of the energy lost by the colliding body A will be. So after the collision, let's say 4m is moving with the speed v1 plus, second is 2m is moving with the speed v2. If they're asking this particular question, they're asking what is the fraction of energy lost by colliding body A. So what is the energy of the A? How much percent of the energy of A is lost? So if we talk about this, we can find what is v1. Direct formula is there. I'll be using that. m1 minus m2 into u1 divided by m1 plus m2 plus 2m2 into u2 divided by m1 plus m2. So we'll be finding the velocity for this one. And what is u2 value? 0. So this product term will become 0. So what is v1? We are getting this. Put the values. 4m minus 2m into u1. What is u1? U divided by 4m plus 2m. 4m plus 2m. So this 2m u divided by 6m. So how much we are getting this? U by 3. So if I ask you what is initial energy, the kinetic energy initial is half into 4m into u square. And what is kinetic energy final of body, same body, colliding body? Half into 4m into, that is u by 3 ka square. So what is the fraction that is lost? So what is the, this is nothing but, this we are getting kinetic energy initial divided by 9 times. Okay, kinetic energy initial divided by 9 times. So how much fraction is lost? The fraction lost Fraction loss is given by 1 minus 1 by 9, that is 8 by 9. Clear? So that will be 8 by 9 because that is kinetic energy by 9, that is a final kinetic energy. Initial is kinetic energy initial. So what is fraction that is lost? 1 minus 1 by 9, that is 8 by 9. So this was the center of mass. We can see the collision, we can see the questions, basic questions they are asking from the collision and as well as center of mass. Let's move our topic, that is rotational motion. So what is rotational motion? If any object is changing its rotation with respect to one fixed particular axis. So right now, if we talk about this will be translation motion. If I fix this particular point and the object is changing its rotation, object is changing its orientation, then will be called as rotational motion. So what are the kinematics of rotational motion we have? So let's revise, make a 2 column, making this side 2 column, this side linear variables, and this side here we have angular variables. So linear variables and angular variables. So what about linear variables we have? We have displacement, corresponding here we have theta. What is theta? So if we talk about this, object is rotating in such a manner that this radius is r and this angle is theta. So this will be linear distance s. So this displacement and angular displacement theta. Here we have linear velocity and here we have angular velocity omega. Time will be same in both the case. Here we have linear acceleration a, here we have angular acceleration alpha. Here we have mass, here we have moment of inertia, that we are going to discuss now. What is moment of inertia? So I am here and this side moment of inertia. Now we'll be using this equation of motion what we have in the kinematics. V is equals to u plus at, where v is the final velocity, u is the initial velocity, a is the acceleration, t is the time. So corresponding, if I write this, what is v? Final velocity should be that final angular velocity, and this side what is u? Initial angular velocity, plus what is a? Alpha, and time will be same. Time is always precious, don't waste your time because time is always precious. Time will be same. So here s equals to ut plus half at square. Second we have corresponding, will be writing this side theta, corresponding theta equals to omega initial t plus half. A will be replaced by, I said a will be replaced by alpha, so half alpha t square. Next we have, that is v square equals to u square plus 2as, corresponding v is the final angular velocity, so that is square is equals to omega initial square plus 2 alpha theta. What is alpha? Angular acceleration, theta is the angular displacement, and omega initial is angular velocity, and this is angular velocity initial, and this is final angular velocity. Like this we have, so this is final angular velocity. These are the kinematics of rotational motion over here. We have the sum of the concept like v is equals to r into omega. We'll be using this also, where v is the linear velocity, r is angular velocity, and r is the radius and omega is the angular velocity. Then we also have at. What is at? R into alpha. Again, r is the radius, at is the tangential acceleration, and alpha is the angular acceleration. Then we have s equals to r into theta. Again, this is the linear distance, r is the radius, and theta is the angular displacement. So these are the equations that we'll be using this. Second, if I talk about, these are the kinematics, how rotation motion happens. We have the different equation for this. And if I talk about the dynamics of rotation motion, so dynamics comes under the forces and the torque. If you talk about, so again, if I say this side linear variables you make, this side linear variables, and this side we have angular variables. So this side linear, and this side let's make the angular variables. So if you talk about the mass, the brother of the mass in rotational motion is given by moment of inertia I. So this will be I. Next we have force. What is force? Newton's second law, mass into acceleration. Corresponding we have torque. What is torque? Torque is the rotational analog of the force. That is moment of the force, also we define torque. So torque is given by mass into acceleration. What is mass? I. Acceleration is alpha. Torque tau is equal to I alpha. We have one more formula, that is tau is moment of the force. So for example, if this about this particular point we want to find the torque, and this particular point force is acting, then here we define, that is this particular distance, the perpendicular distance, that is r perpendicular into f. Next we have linear momentum, that is linear momentum is when mass into velocity. Corresponding we have angular momentum, that is I into omega. Angular momentum I into omega. We have one more formula for angular momentum, that is r mv r perpendicular, mv r perpendicular. And if you write in terms of this cross product, torque tau is given by r cross f. And if you write this in terms of the cross product, it will be L equals to R cross P. L equals to R cross P. Then here we define kinetic energy. What is kinetic energy? Kinetic energy translation is given by half m v square. Replace the mass with I and v with omega. Then kinetic energy rotation is given by, the rotation kinetic energy is given by half I omega square. Okay, half I omega square. That is the rotational kinetic energy. If you apply the work energy theorem, what is work? What is work? We discuss force into displacement in terms of the linear. And what will work here? What will work in this case of angular? The work will be given by, so force dot displacement, that is a work done. We can also write here F dot integration of this F dot ds. So here F dot ds integration is also work. Corresponding work done, here we can write work done equals to tau into theta. Tau into theta. Corresponding we can write here W equals to integration of tau into d theta. So tau into theta, that is work done in this particular case. Rotational kinetic energy we got, that is half I omega square. What is I? Moment of inertia. So moment of inertia for any body we define as I is given by mk square. What is k here? K is the radius of gyration. So moment of inertia will be different in terms of the r, but in terms of the k it is always mk square, where k is the radius of gyration we have. We also have torque, we also have force. Newton's second law if I write in this particular term, that is F equals to dp by dt. So corresponding F is replaced by suppose torque, then torque, and P is replaced by, what is P is replaced by L. So this torque is given by dl by dt. If force is 0, then we define that in the Newton's law, that is momentum will be constant. So if torque is 0 here, if torque is 0, whatever the torque that is acting, that is 0, then here we define that this particular term will be 0, then L value will be constant, the angular momentum will be constant. If the net action torque acting on the system is 0, then L will be constant. So these are the rotational motion basics we have. Next we have types of the motion. Again I tell there are 3 types of motion. First one is translation motion. Second is rotation about fixed axis. Rotation about fixed axis. And third one we have the combined rotation and translation motion. Combined rotation and translation motion. So translation motion means if object is moving like this way only. So this object is moving in a straight line without changing its orientation will be called as translation motion. What is rotation motion? About fixed axis, you fix one particular point and rotate the object like this. So whatever the motion that we are getting, that is rotation motion. You are fixing this particular point, it is rotating. You are fixing this particular point, it is rotating. So this will be rotation motion. Next we have combined rotation and translation. So object will be rotating as well as it will be moving forward. After some time it will be like this. After some time it will be like this. After some time it will be like this. So this will be defined as it is rotating, it's changing its orientation as well as it is moving forward. This combined translation rotation motion. In this case, a special case in our syllabus is that rolling motion. So what is rolling motion? So let's just discuss a little bit, then we'll move on to the questions over here. So if we talk about the rolling motion, so rolling motion is the combined translation as well as rotation motion. So if there is a disc on the floor and this disc is moving forward with velocity vcm, so all the points which will be having velocity vcm, all the points will be having velocity vcm, it is just translating. At the same time you rotate this as well. So this one is translating, at the same time you rotate this as well. So if you rotate this, this will move with omega into r because of its rotation. If it is doing pure rotation, omega into r this side, the velocity will be omega into r. This particular point will be having velocity omega into r. If it is rotating with angular velocity omega into r. Second, if I combine this, so this one is pure translation. So this is pure translation motion, and this one is pure rotation motion. If we combine this translation as well as rotation motion, what will happen? We'll be getting the rolling motion in which the object will be rotating as well as, and it will be moving forward as well. So as it is moving forward, it will be having velocity of center of mass. It will be moving with velocity of center of mass in forward direction, but because of its rotation, it will also have velocity vcm plus r omega. This is vcm plus r omega, and this particular point vcm velocity is forward, but r omega velocity is backward. So this particular point velocity will be given by vcm minus r omega. And if we compare this pure rolling motion on the ground, on the static ground, pure rolling on ground. So what will this particular point of contact should be having velocity 0. So if you talk about the pure rolling motion, if the object is doing pure rolling motion, the topmost point is having velocity 2 vcm. This particular point is having velocity 0. Net velocity will be 0. This particular point velocity vcm in forward direction, this vcm in downward direction, this side root 2 vcm. This particular point is having velocity vcm in forward direction, this side vcm in this direction, this side root 2 vcm. So this is the rolling motion. And if they're asking what is acceleration of different points, just replace vcm by acm, but where acm is the acceleration of the center of mass, acceleration of center of mass. So let's solve some of the questions from this moment of inertia. So moment of inertia is given by mr square for single particle. If the particle is moving in a circle, this radius is r, the mass is m. If multiple particles are there, the moment of inertia is given by summation of mi into ri k square. If we have the ring about this particular axis, what is moment of inertia? mr square. If you have disk about the same axis, the moment of inertia is given by m equals to m into r square by 2. If you have hollow sphere and it is rotating about this diameter, that is hollow sphere is there, this will be 2 by 3 mr square. And if you have solid sphere, the moment of inertia of the solid sphere about its own axis, that is I is equals to 2 by 5 mr square. 2 by 5 mr square. So here we define that is radius of gyration, always just equate I equals to mk square. So the radius of gyration of solid sphere of mass m kg about xy is 5 centimeter. So about this particular point, about this particular axis, they are asking what is the radius of gyration. They have mentioned the radius of gyration. They are asking what is the value of the x, 5x root 7 meter. So let's say what is moment of inertia about this? As this is which is sphere, solid sphere, we can write here moment of inertia about this particular axis, that is ICM. About this particular axis we will be writing this IXY. IXY will be given by ICM plus MR square. What is MD square? This is the parallel axis theorem we have. So this M into D square. So just putting this value, this will be 2 by 5 MR square plus M into D. What is D? Distance, that is M into 5 square. So this is IXY, and this equate this with MK square because this is the moment of inertia. Putting the values here, M cancel everywhere. What is K value? Radius of gyration dimension is how much? 5. So this side here we have 5K square, and this side here we have 2 by 5 into R square. What is radius? The radius dimension is, the radius of gyration dimension is this much. The radius of sphere is 5 root x. 5x root 7 whole square plus 25. So we are getting this. So if we solve this particular case, m into d square. So this m is cancel everywhere. So we are getting this. Radius of gyration is 5 meter square. M into this radius is, this distance is, again this will be 5 root x ka whole square. So we have to solve this particular case. So 5 root x ka whole square. So we can note down this. We are getting this 5 square, that is 25, and this is 1 plus 2 by 5, 7 by 5 into this square, that is 25 x square divided by 7. This get cancelled, this get 5, and this is 5. So we are getting this 5 is equals to x square. So what is x? Root 5. The value of x here we got it as root 5. So moving next question over here, again the question is coming from the moment of inertia. Here we have uniform rod of mass m, length is L, about an axis passing through its midpoint and perpendicular to length is I naught. So moment of inertia about the center of mass they mention is I naught, and they're asking what is the moment of inertia about an axis passing through one of its end and perpendicular to its length. About this particular axis they're asking moment of inertia. So what is moment of inertia about this particular axis using the parallel axis theorem? So this IAB we can write here ICM plus MD square. So what is ICM about this axis that is passing through its center? They mention that is I naught plus this axis and this axis are parallel. Distance between them is how much? L by 2. So this will be writing M L by 2 ka whole square. So this will be given by I naught plus ML square by 4. The answer is I naught plus ML square by 4. L is the length of the LEC length. So what we have to focus in this case? We have to focus that two axes would be parallel to each other and one axis would be passing through center of mass. Then we can calculate. Moving next. The ratio of the radius of gyration of thin uniform disk about an axis passing through its center and normal to the plane of the radius of gyration. The ratio of the radius of gyration of thin uniform disk about an axis passing through its center. The ratio of the radius of gyration of thin uniform disk about an axis passing center and normal to its plane. So there is one axis like this. As per the given question, there is one axis like this and one more axis to the radius of gyration of the disk about its diameter. So about its diameter, if you rotate about this, so this particular diameter lies in the same plane. So moment of inertia for this we already know what is that. For the disk, mr is square by 4. But this particular axis, that axis is perpendicular to its plane. So for this, moment of inertia is given by I is equals to mr is square by 2. So m k1 is square and this is m k2 square. They're asking what is the ratio of k1 by k2. What is the ratio of k1 by k2? So I'll be writing this m k1 is square by m k2 square equals to this side mr square by 2 divided by mr square by 4. So this mr square cancel, we are getting this mr m also getting cancel. So k1 by k2 ka whole square we are getting this 4 by 2, that is 2. So what is k1 by k2? The k1 by k2 will be writing this root 2 raised to 1. So this is the radius of gyration for this case. Second, let's move to some more term, that is dynamics of the rotational motion, that is torque. So what they are asking, the moment of the force F is given by 4 I cap plus 5 j cap minus 6 k cap about the point 2 comma 0 comma minus 3. Force is acting at this particular point. About the point they're asking, so 2 points that we have to consider where the force is acting and about the force, about the torque we have to, about which point we have to calculate the torque. So this particular point, let's say this particular point where the force is acting, so point P where the force is acting. So this, what is force that is acting here? 4 I cap plus 5 j cap minus 6 cap. And what is this particular point having coordinate? 2 comma 0 comma minus 3. Let's, about which we have to calculate. So this particular point Q is there and Q is having coordinate 2 comma minus 2 comma minus 2. We have to find, so we have to project the position position vector from this point Q to point P, and what is that R, where about at which point the force is acting, and from where we have to calculate the torque. So joining this point Q and P, so R vector will be given by this, we'll be writing this R vector final minus initial 2 minus 2 I cap plus final minus initial 0 minus of minus 2 j cap plus final minus initial minus 3 minus of minus 2 k cap. So this R vector that will be writing here, this will be 0 I cap plus 2 j cap minus 3 plus 4 plus k cap. So this is R vector we are getting. And if they're asking torque, and what is torque? Torque is given by R cross F. Torque is given by R cross F. So we'll, from there we can calculate torque tau R cross F. So that's it. I cap, j cap and k cap, and this will be 0, 2 and 1. And this side force, what is force that is acting? 4, 5 and minus 6. So I am telling you to, giving you to solve this particular problem, that you know the cross product, right? So we can solve this using this. Moving next question. A constant torque of 100 Newton meter turns a wheel of moment of inertia 300 kg meter square. So moment of inertia they have given I is equals to 300 kg meter square. About an axis passing through its center, starting from the rates, its angular velocity after 3 seconds. So starting from rates t is equals to 0, initial angular velocity is 0. After some time t is equals to 3 seconds, what is final angular velocity? Omega initial plus alpha into t. But from where we calculate the alpha? From here we will calculate the alpha. That is torque tau is equals to I into alpha. Calculate alpha from here, substitute there. That's it. This, how much torque is acting? 100 is equals to I, that is 300 into alpha. So what is alpha? 100 by 300. So this side, if you put this, omega final is given by omega initial. So what is omega initial? 0 plus 1 by 3 into time. What is time? 3 seconds. So we are getting this. Omega final is given by 1 radian per second. So that is final angular velocity will be 1 radian per second. Moving to next question. Again the question is coming from the torque. A rope is pulled around a hollow cylinder of mass 3 kg and radius 40 centimeter. What is the angular acceleration of the cylinder if the rope is pulled with a force of 30 Newton? So there is one cylinder. On the cylinder we have the rope as well. So rope is pulled with how much force? The rope is pulled with a force of 30 Newton. What is the angular acceleration of the cylinder if the rope is pulled with a force of 30 Newton? So this side, what is the radius? The radius that they have mentioned is 40 centimeter. That is 0.4. So if we talk about this torque, what is torque? R perpendicular into F. Because of this force, torque will be acting. And how much? What is R perpendicular? This radius will be R perpendicular. So tau is equal to this side 0.4 R cross F. It will keep on rotating like this. R cross F. So 0.4 into F. That is 30. Okay. What is angular acceleration they're asking? So 0.4 into 30. That is tau. So this 3. We are getting this. That is 12. And what is 12? I into alpha. And what is I here? Hollow cylinder is there. Hollow cylinder is similar to ring. What is moment of inertia? I is given as mr square. So I is mr square. So mass is given. What is mass? 3 into radius is given 0.4 ka square. So putting this value over here, moment of inertia 12 equals to 3 into 0.4 into 0.4 into alpha. 10 by 0.4. 10 by 0.4 equals to alpha. So this 100 by 4 answer is 25 radian per second square because this one is alpha. Next we have rotation. The question is coming from rotational kinetic energy. So if we talk about the rotational kinetic energy, a solid cylinder of mass how much? 2 kg and radius 4 cm is rotating about its axis at rate of 3 rpm. So 3 rpm, that is 3 into 2 pi by 60 radian per second. Remember this, rpm. 1 rpm is 2 pi by 60. The torque required to stop after 2 pi revolution. So what is initial kinetic energy? The initial kinetic energy. What is final kinetic energy? We can note down this work energy theorem. Here we can apply work energy theorem. So if you apply the work energy theorem, the kinetic energy final minus kinetic energy initial is equal to work done by the torque. And what is work done by the torque? What will work done by the torque here? That is integration of, that is not required, integration part is not required here. Torque multiplied by theta. Just like force into displacement, here torque multiplied by theta. And as it is stopping, this will be minus over here. So kinetic energy final minus kinetic energy initial if I ask you. So what is kinetic energy final? That will be 0. And initial we have to calculate from here. That is kinetic energy initial is given by half I omega square. Half I omega square. Again the solid cylinder is there. It is similar to disk. So kinetic energy initial is half into mr square into omega square. Putting this value, we'll be writing this minus half mr square into omega square is equals to minus tau into theta. So they're asking the tau. So put the values over here. So I'll be writing this minus half into mr square into omega square equals to minus tau into theta. What is theta? 2 pi revolution. Again 2 pi revolution. Revolution means 2 pi into 2 pi radian. So 2 pi into 2 pi radian. So solving this minus minus it will be plus. So this half into what is the mass they have mentioned? Mass is 2 kg. Radius is 4 centimeter. 0.04 ka square into omega. What is omega? This one is the omega. So if I do the omega square, so omega is square 10. So this pi by 10. Omega square means pi square by 100 is equals to tau into 4 pi square. Pi square cancel. From here we'll be calculating this. This 2 and 2 also getting cancelled. 0.4k square, that is 0.16. 0.4k square, 4k square, that is 16 into 10 to the power minus 4 divided by 4. We are getting this. So we are getting this, whatever the value we are getting here, 0.4k square, 16 into 10 to the power minus 4 into 16 into 10 to the power minus 4 divided by 4 we'll be getting this divided by 100. So this one is tau something we are getting. So as we are getting in the order of -4, and this side here we are 100. So this will be in terms of the order of -6 we are getting. That's 2 into 10 to the power -6. So a solid sphere is rotating. A solid sphere is rotating freely about its symmetry axis in free space. The radius of the sphere is increased, keeping its mass same. So it is rotating freely means net torque is 0. Net torque is 0. If the net torque is 0 means what? Tau net is 0. What is tau net? That is dl by dt. This will be 0. So when this net torque is 0, so from here L will be constant, right? What is L? Angular momentum. So net torque is 0, angular momentum will be constant. Angular velocity might change. Solid sphere rotating freely about symmetry axis in free space. The radius of the sphere is increased, keeping its mass same. So if it is solid sphere, I is equals to m r square into 2 by 5. Here we have moment of inertia is given by 2 by 5 mr square, keeping its mass same. Mass is same, but radius is increasing. As the radius is increasing, moment of inertia will also increase. And as the moment of inertia increases, kinetic energy rotation is given by half I omega square. I is increasing, so this will also increase. Second is angular velocity. As L is constant, so here we can write L equals to I1 omega 1 is equals to I2 omega 2. So in this case, moment of inertia is changing, so angular velocity will also change because angular momentum has to be constant. So this is also changing. So answer is this one, that is this will be constant. A particle of mass m moves in xy plane with a velocity along this straight line AB. If the angular momentum of the particle with respect to origin O is LA, then it's at B, and LB when it is at B. So at this particular point, when the particle is over here, the particle is moving on this particular line. This is moving this way. So angular momentum about the origin. So if we talk about the angular momentum of moving particle is given by mv into r perpendicular. If the particle is moving in a straight line, then velocity, anyway velocity they have not mentioned, they have mentioned moves in x with velocity v, means they have mentioned constant velocity. M is constant, v is constant. What is r perpendicular? The perpendicular distance of the line of the motion of the particle from the origin. So the particle is moving along this particular line, so this will be the perpendicular distance. If the particle is over here also, over here also, over here also, over here also, the line of motion of the particle and this perpendicular distance will be same. So r perpendicular is constant. So in this particular case, what happened? L will be constant. And let's look at the option, what option is saying. So if the particle is moving in a straight line, you can note down this. The particle is moving in a straight line, the angular momentum about the origin or about any particular point will be constant if it is moving with constant speed. Because r perpendicular, this is the line of motion of the particle, and from the origin this will be r perpendicular. So this will be constant. So let's look at the options. LA is equal to LB. The relation between LA and LB depends on the slope of the line. No, it will be constant anyway. Conservation of angular momentum. Question is coming. A thin circular ring of mass m and radius r is rotating about its axis with constant angular velocity omega. Two object is up. So there is one ring. This ring having mass m. This ring has, let's say this ring is having mass capital M and radius is r. Initially it is rotating with constant angular velocity omega. It is rotating with constant angular velocity omega about its own axis. So if I ask you, what after some time what is happening? Two objects of each of mass m are attached gently to opposite ends of the diameter of the ring. So two objects are attached like this. So this side one mass and this side also one mass is attached like this. Obviously what will happen? The speed of rotation will decrease, right? The speed of rotation has to be decreased. We are putting mass on the ring. So what is the initial angular momentum? I into omega. Because we are putting gently, each and word is important. We are putting here mr mass attached gently. So when you are putting gently means we are not applying the force. If you are not applying the force, there will be no torque. The torque is 0. So angular momentum will be constant. What is initial angular momentum? Should be equal to what is final angular momentum. That's it. So this Li should be equal to Lf. What is Li? I into omega should be LF. What is LF? IF into omega F. So what is I? Moment of inertia, that is M R square, capital M R square into omega. And what is IF? The final angular, the final moment of inertia for this mass, that is mr square. Mr square plus this one is moving in a radius r, this also moving in a radius r. This will be, both are moving in a circle. This will be 2m r square into omega final. So mr square cancel. Sorry, we can't cancel because masses are different here. So here we can write r square cancel. So what is the final angular velocity? That will be writing m into omega divided by this side m plus 2m. That is the final angular velocity. Answer is option D, m into omega. So that's it for today. So tomorrow we'll be discussing what is the next chapter is gravitation we have. Then what are the gravitational forces and field. Next also we have acceleration due to gravity as well. Gravitational potential and energy and satellite. So in this tomorrow chapter, the chapter is easy. The chapter is having little weightage. We can expect one question from that. So please do attend those tomorrow's class as well. And mostly questions will be coming from acceleration due to gravity as well as gravitational potential and satellite motions, as well as is there, that is what is gravitational potential energy, what is gravitational potential and satellite motion. So that's it for today. We'll be coming back with this chapter tomorrow. So till now, be prepared and do your best. All the best.